so mild this winter and this room being so cold, but there it is, I've already done it. Anyway, it's my pleasure to introduce and welcome today's speaker, Dr. Jaehan Bae. Jaehan is a postdoctoral fellow at the Carnegie Department of Terrestrial Magnetism. He did his BS and MS degrees in astronomy at Seoul National University in South Korea. He did his PhD in astrophysics at the University of Michigan under the supervision of Lee Hartman. After his PhD, he took a Vera Rubin postdoctoral fellowship position at Carnegie DTM, and then after 2 years won a prestigious NASA Sagan Fellowship, and he elected to stay at DTM to continue there. Jaehan is an expert in numerical simulations to interpret multi-wavelength observations of protoplanetary disks to help us understand planet formation and evolution, and I think that's what he's going to talk about today. Jaehan.
Yeah, thanks so much, Jacob, for the introduction, and thank you everyone for coming to my talk. Yeah, it's been a pleasure to be here at Chicago. This was actually my first visit to Chicago in the department, and I'm really enjoying talking to many of you, and I'm looking forward to talking more with you this afternoon. So, yeah, while you're enjoying your pizza, I guess I'll talk a little bit about planet information. So, let's start by asking this question of why should we care about planet information? Well, part of the reason is that we are making more and more problems rather than solving problems. So, yeah, that's part of it. But seriously, why should we care about information, right? First, it is one of the most fundamental questions in astronomy and perhaps across all science fields. Even if you are not working directly on planet formation, you might have wondered at some point in your life, how did solar system planet forms, right? Including the Earth. How did it form and why are we sitting here today, right? And the other question is, planet formation is linked to life. So how did life begin on Earth? And how in general does life begin? And do we have life elsewhere in our solar system or in our galaxy or in the universe, right? If there's life elsewhere, then in which form? The second is that we now know that planet formation has happened in the past, at least in our galaxy, right? In solar system, we have 8, perhaps more, including hypothesized planet 9, if you're interested. We have 8 plus planets, so we know that it has to happen in the past, 4.5 giga-years ago, approximately. And we know that there are more than 4,000 exoplanets orbiting around other stars than the Sun. And this is one way to present the exoplanet population. On the y-axis, I'm showing you a cumulative number of detections as a function of discovery year, and different techniques are represented with different colors. This is another way to look at the exoplanet demographics. On the y-axis, it is plotting planet masses with units of Jupiter masses. So this is one Jupiter mass here. On the x-axis, this is semi-major axis of those planets for orbital separation from their host stars. So this is 1 AU, and both axes are in logarithmic scale. So I can now ask a couple of questions about this diagram, right? I'll get back to this later on. But the first question I'd like to know is, I'd like to answer is, how did they form? How did these exoplanets form? And where in their parent protoplanetary disk those planets formed, right? And if you look at those population, they are very close. Many of them are very close, within about 1 AU. And these are hot Jupiters with masses of about Jupiter masses. And these are what are known as super-Earth, mini-Neptune, or sub-Neptune. And we don't see those planets in our solar system. So that brings this question of, do we have one ubiquitous mechanism that can explain both solar system planet formation and exoplanet formation? Or is there some other mechanism, different mechanism to explain different populations? And lastly, what I'm going to tell you today mostly about is that we are now observing samples of planet formation in protoplanetary disks. So this is really the game changer right now, and this is workhorse actually, which is ALMA, large millimeter, sub-millimeter array down in Chile. And one of the very first long baseline observation made with ALMA during science verification is this famous HL tau image. So what are we looking at in this image? So this is a disk around the young star HL tau, which is about 1 million years old. So the star is at the very center of this disk. And we are looking at the thermal emission coming from the solid particles embedded in the disk with sizes of order of the wavelength of this observation, which is about 1 millimeter. So you're basically looking at grains, cent-sized grains within this protoplanetary disk. To remind you that protoplanetary disks are not two-dimensional objects, but they are three-dimensional. They have three-dimensional geometry. So here is a central star, and it has this shape, of course, but you have this three-dimensional vertical direction geometry. And it's a mixture of gas and dust, and we are looking at pretty large dust, millimeter-sized particles. They tend to settle down to, well, close to the middle plane, so we are literally looking at the region around middle plane. And the disk is, of course, in this case, inclined in this direction, and we see a set of bright and dark rings. Okay, just to give you some sense what it looked like with previous generation radio array. This is for the same object, HL tau, in same size scale, 100 AU, this is 100 AU, but taken with previous generation radio array, Karma. And the paper was not too long ago, 9 years ago, 2011. And you can see that, well, in general, we knew that there's a disk, right? But with this resolution, special resolution, this is the size of the beam, or let's say special resolution element, we were not able to see all these fine structures. And we started looking at more and more of these substructures in protoplanetary disks. So this is data taken as a part of D-sharp survey, which is disk substructures at high angular resolution projects, where we had few AU spatial resolution. And if you look at each of these disks, they are just not boring, just blobby disks, but they all have, pretty much all of these have structures. The most common ones are rings and gaps. They are pretty concentric, but in a few cases you also see these spiral arms in this case, and this one as well, and this one, which is almost looking like spiral galaxies. So the question is then, what has created these protoplanetary disk substructures, right? Planets can offer a very compelling explanation, because if you look at this simulation, which is 3D hydrodynamic planet disk interaction simulation, you are looking at only 1/4 of the entire disk, and this is the disk middle plane, density distribution, and here's the planet, and this is the axion view along this azimuth, including the planet. And you can already tell that the planet excites a pair of spiral arms. You can also see from this side. And it opens a gap around this orbit and clearing material around this orbit. So gaps and spirals, those are two fundamental outcomes, most fundamental outcome of planet disk interaction. Of course, if you ask if we can detect those structures or not, that's another problem, but at least those are very basic outcome of planet disk interaction. So now, if we believe these substructures that we observe nowadays, then you can ask, can we infer any properties of planets? One way to do that is forward modeling. So we have this observation. This is one example I will explain in more detail later in my talk. So don't worry too much about the details, but this is CO observation taken with ALMA of a system called PDS-70. So you are basically looking at how gas is distributed on sky, and this is continuum observation. Again, you are looking at continuum emission coming from millimeter-sized particle embedded in that disk. Then you can try to reproduce these observations by running simulations. In this particular case, I took two Jupiter-mass planets, and this is gas distribution, and this is solid particle distribution. Those are test particles. And then you can then run radiative transfer calculation, post-processing, to reproduce the observation. So these are a reproduction of these two observations, and I'll get back to this subject later on. So going back to this diagram of exoplanet demographics, now what we can then do is, we have tens of these disks with substructures. In some cases spiral arms, in some cases rings and gaps, and you can try to reproduce these observations by inserting a planet or planets in disks with substructures. And I've collected from literature, including some of mine, where we as a community try to reproduce these observations, and this is the result. So with red symbols, these spiral symbols, those are the ones, the planet parameters, the masses and semi-major axis to reproduce disks with spirals. These ones, blue symbols, they are what is required to reproduce the observations with rings and gaps. So each dot or each symbol, they represent one hypothesized planet. And it's really interesting because when you look at the distribution on this diagram, they are not overlapping with the exoplanet, currently detected, currently non-exoplanet. So this raises the question of how would they evolve over time in next million years or billion years? Would they stay there, or would they stay but they will grow to multi-Jovian mass planets? Or would they evolve in such a way that they migrate inward, orbital migration? And would they gain some mass to become a hot Jupiter or cold Jupiters? Or would they lose some of their atmosphere and become super Earth or sub-Neptune-sized planets? So I've shown you some of state-of-art observations of protoplanetary disks, but to summarize some motivating questions for my science, these are top three of the questions. So we know that exoplanets are common. We commonly see exoplanets, but the question is how and where did they form in the first place, right? We see a lot of substructures of disks, but what has created those disk substructures? We don't have an answer to that yet. And what can we learn about planet formation processes when we have these gorgeous state-of-art planetary disk observations? Those are three main questions that is motivating my science these days. So to start with, let me ask this question of what creates rings and gaps in protoplanetary disks. So this is one example, HD 1692, 3296, and you see multiple sets of dark gaps and bright rings. Well, one natural way to explain this is, well, maybe something is clearing this part of the disk, so you physically remove grains from this dark part of the disk and you add those material in this bright side. So you have more material in the bright part of the disk, you have less material in the dark side of the disk, which makes perfect sense. But we are looking at dust particles. This is dust continuum. So we need to understand how those particles would interact with this gas. Again, protoplanetary disks are a mixture of gas and dust, and typically it is understood that we have a lot more gas than the dust in terms of mass. So if there are only dust particles around the star, so here's my star, and these are dust particles, they will rotate at the Keplerian velocities, just gravity and centrifugal force, right? If I have only gas, right, this is my gas disk, what gas will do is it has the same gravity, right? But then in protoplanetary disk, it's usually hotter closer to the star, and you have more material closer to the star, which means that you have higher pressure in general near the star than the outer disk. So there's this pressure gradient or pressure support. So in order for these three terms to be balanced to each other, what will happen is that the gas will try to rotate slightly slower than Keplerian velocity just because of this pressure term. So gas is rotating at the Keplerian velocity. Now, when you have gas and dust, dust will try to rotate at Keplerian velocity while gas is rotating at the Keplerian velocity. So from the point of view of this particle, it will feel headwind and it will lose angular momentum and it will spiral into the inner disk. Now let's assume that you somehow reverse the pressure profile such that you have higher pressure in the outer disk than the inner disk, right? Then what will happen is your gas is now rotating at super Keplerian velocity, and in that case your dust particle will feel tailwind so that it will migrate outward. So in this set of numerical simulations, what I did was I had some gas. This is gas surface density distribution in a disk with sizes of 100 AU. This is a smooth power law type disk. And in this one, I put arbitrarily some sinusoidal correlation in density profile. And these are different particles with different sizes. And when I let it go, you will see that particles will fall into the inner disk and time scale is as a function of time, but for this case where you have a lot of pressure maximum and minimum, you see that particles are collected in this pressure peak because of the aerodynamic drag. So that's one possibility, but that's not the only possibility. You can think of thermochemical origin. So what it is again, we are looking at thermal continuum coming from those particles. So it might be possible that if you somehow change properties of those particles for whatever reason, then you may expect to see these structures. One popular idea is ice line or snow line. So again, you have central star, temperature decreases outward. So for example, you can think of, say, water. So here is water ice line, inside of which water is present in gas phase, right? And outside of which water is frozen onto those grains. And around this boundary between gas phase water and ice phase water, you expect to see some difference in size. First, size of the particles. Second, opacity of the particles. Third, the total amount, total mass in the solid particles. Okay? So in this paper by Kokojang, they try to explain three main gaps in HL tau disk by introducing three ice lines. This one is for water, this one is for ammonia, and one is for CO. And they nicely explain the gaps, the three gaps in the HL tau disk. But one thing I'd like to point out here is that in this case, it's just only for grain properties, and the total gas pressure is not expected to change across these ice lines. And that is because almost all the gas is present in the form of hydrogen molecule, H2, right? And even if for the most common molecules in protoplanetary disk, carbon monoxide, the abundance ratio between CO and H2 is less than 10 to the minus 4. What that means is that even if you evaporate all the CO ices, certainly it will increase the total gas pressure by a factor of 10 to the minus 4. So it's almost invisible. So we came up with this idea of looking at the gas pressure, because in this dynamic origin case, we expect to see gas pressure changing across these rings and gaps, whereas in the other case, if it's just grain opacity or grain size or grain properties, then we don't really expect to see gas pressure changing across these structures. So let's do it. How can you do that? So here's this profile, gas pressure profile as a function of radius in this cartoon. So when you have smooth profile, it's more or less Keplerian velocity. But when you have a minimum, so it's like a gap in the disk, then what will happen is that at the center of the gap, it will be more or less Keplerian. But if you look at this side of the gap or the other side of the gap, the pressure gradient, this term here, now again, this is the centrifugal force, gravity in 3 dimensions, and this is the pressure support. So if you look at here, pressure drops very rapidly over radius, which means that this term is negative and large negative term, which means that the rotation velocity should be smaller than Keplerian. So we expect sub-Keplerian rotation velocity at this position in radius, whereas in this part of the gap, we expect to see, because this is positive gradient, this is now positive term, so it is added to the gravity, so we expect to see super-Keplerian rotation profile. So you expect to see this characteristics of Keplerian to super-Keplerian rotation profile. When you have a bump pressure peak here, right, then the opposite can happen, right? So you expect to see pressure, you expect to see super-Keplerian velocity to sub-Keplerian velocity. In practice, how do we measure rotation velocity with Raman, right? You have this Keplerian disk, it rotates fast in inner disk, it rotates slower in the outer disk. When it is based on the line of sight velocity is 0 everywhere, which means that there's no redshift or blue shift, right? But when you incline your disk, in this particular case, around this axis, you tilt this side of the disk toward us, right? And this side of the disk far away from us, then you will see blue shift, because this part, the material is coming toward us, and this part you expect to see red shift. And this is what the real data looks like for this HD 16396, and this is CO9, And you can think of it as a spectroscopy for these line emissions, because we have very narrow line in terms of frequency or wavelength or velocity. And if you look at a certain velocity, that will give you a feature that is coming from certain position in the disk. So at this velocity, you are looking at only this part of the disk. For example, at this velocity, you are looking at only this part of the disk, and this is a three-dimensional view of that. So this is the upper part of the disk. So again, this is 3D geometry, so you need to think about as a flared disk. So this is upper side of the disk, this is the lower side of the disk, and you are looking at this isovelocity contour with this observation here, and this blue part here is far side of the disk you are looking at here. Okay, so you can now look at each pixel in the sky and infer the velocity, line of sight velocity of this. And then this is what it is. So you have line of sight velocity from 4 to 7 kilometers per second in this case, and you see what is exactly expected, right? And then what you can do then is to first infer the emitting surface. This is 3D geometry, so it is flared, and pick a annulus, right? This is the points where you have same distance to the center star, and deproject the profile, velocity profile, to get the rotation profile at this radius. And you can do that for the other radii as well. And this is what you get. So this is again for this disk. Again, remember that we expect for these gaps sub to supercapillarian transition. And if you have pressure peak, you expect to see super to subcapillarian rotation profile. And this is what it is, right? Rotation profile subtracted, capillarian velocity subtracted rotation profile. So zero means capillarian rotation, negative value means subcapillarian, supercapillarian as a function of radius. And these locations are where we see gaps in millimeter continuum. And as you can see, let's do this one first. So you see this gap, and you see this subcapillarian to supercapillarian rotation velocity transition. And you also see same feature around this gap and around this gap as well. And in between, where we see bright rings here and here, it changes from supercapillarian to subcapillarian. So it is really strong evidence that there are local pressure maximum at these locations or minimum at the locations of the continuum gap, suggesting that those particles are actually trapped in pressure peaks in the disk. And you can go one step further and try to look at what the vertical velocity looks like. So this is action view of the disk, and you are tracing certain locations, certain height in the disk, because CO is optically thick, you are not see through the disk, and you are just tracing the surface. And at the surface where we are probing the disk, you see this vertical drop of the CO gas. And what we think happening here is actually, it has been predicted for many, many years in numerical simulations. When you have a planet here at the middle plane, it will try to open a gap, right? And then the disk will try to recover that smooth density profile, so you expect to see some vertical infalling motion at the location of the planets. So to support this observations, I ran three-dimensional hydrodynamic simulations, and what you see here is the middle plane density, and you see 3 planets. And what I have plotted here is the rotational velocity. Blue means subcapillarian, red means supercapillarian, and at the locations where I put the planets, you see the transition from subcapillarian to supercapillarian, which is exactly what is expected and exactly what we are observing. And you can see the vertical velocity fields are converging down to the middle plane, which is also what we see from the observation. So the bottom line from this work is that while we see particles trapped in pressure bumps, and planet is one possibility, very intriguing possibility, but unfortunately this is not the end of the story, and that is because, well, I like planets, and I work on planets a lot, but there are other possibilities that can generate those pressure bumps, pressure maximum, pressure minimum. It includes some fluid instability. It can be generated by some magnetic activity or winds. So we cannot really conclude that these are formed by planets just by looking at pressure profile. And to make the things worse, what I'm showing here is that one planet can create multiple rings and gaps, and I will show what's going on here. So I put one Jupiter-mass planet here at this location, and there are a lot of things going on, but one thing I will highlight is there's one main gap, which we typically see. But if you look at the inner disk, right, there are additional gaps, this one. In this case, one planet created 3 gaps in the protoplanetary disk. So what's going on here, right? So in order to understand this, let's go through a little bit of dynamics, planet disk interaction. So first thing I'd like to highlight here is that one planet, a single planet can excite multiple spiral arms. It has been seen in numerical simulations since 1990s, but we didn't understand why it happened until I showed this in 2018. So the planet in this case is right here, and you see that there is a spiral directly connected to the planet, but in the opposite side you see another spiral exciting here. So there are 2 spirals in this case. So I don't want to go into too much details. I don't want to do linear analysis in my talk. So I'm not going to do that, but I have a version, probably unreached top version of it. So I hope this works. So it's similar to how a boat creates waves on lake. You should know this because you are close to right? So when you sail on a boat, right, it will create 2 lakes in this case, right? It is pretty similar, actually. Why you see 2 wakes behind you is because you are moving forward, or in other way, if you're seeing here, the water is moving away from you, right, from the point of view of this boat, right? One thing different from this analogy and protoplanetary disk planet disk interaction is that protoplanetary disk is a differentially rotating disk, right? This is just showing you that rotation velocity is as a function of the distance from the central star. So in this case, disk is rotating faster in the inner disk, slower in the outer disk, right? So now I can cut this figure and make it like this, so that this part of the water of the lake goes this direction, and the other side of the disk, the lake goes in the other direction, which is pretty similar to this, right? So now you can generate 2 nicely formed spirals, which is pretty similar to this diagram, right? On top of that, why do we have multiple spiral arms, right? That is because protoplanetary disk is again rotating differentially. You have this differential rotation, and that's why you create more than just one, okay? So in a nutshell, it's differential rotation, but what can a spiral arm do, right, physically, dynamically? Because it is connected to the planet, it rotates at the speed of the planet, which means that if you are sitting here in the gas disk, you will rotate at a different speed as from the speed of the spiral arm. What that means is that you have spiral arm, gas will pass through the spiral arm, and you can get shocked. So it transports angular momentum through shock dissipation, and it can open a gap. Now I showed you that we can form multiple spiral arms with one planet. Then now I can ask this question: what happens when a planet excites multiple spiral arms, right? Then the answer is the planet can open multiple gaps. That's what's happening here. So if you look at this figure again, it excites 2 primary spiral arms, one this one, and the other one here. They together open the main gap, the primary gap, but there are 2 additional spiral arms at this location, and at this location, those 2 are what is opening the additional gaps. So this is one of the D-Sharp survey paper that came out in 2018. And what the authors tried to do here is that this is one of the disks where they see multiple rings and gaps. And to reproduce this one, again, this is forward modeling. What they have done is they put one single 0.1 Jupiter-mass planet at this location, 99 AU from the central star, just one single planet. And if you compare those 2, it's looking pretty similar. And this is the radial profile. With blue, that's actual observation. The orange is showing you the intensity from the simulated observation. So it is very compelling, but now this is really me sitting in front of the desk making more problems because I was trying to interpret this with planets, right? If you have two gaps, then I just put two planets, one in each gap, and well, things are done, right? But that's not the case. The number of gaps, number of observed gaps, they are not necessarily the same as the number of planets. Two planets can open two gaps, one planet can open two gaps. Zero planet can open two gaps, it's not planet, right? So I'm making the problem worse. So then what should we do, right? We really need more direct evidence of planets themselves. So these are some possibilities. Those forming giant planets, they can be hot, several hundred K or even beyond 1,000 K. So you expect to see thermal emission, which is typically in near IR. So that's one way. One other way is if those planets are accreting material, either circumplanetary disk material or circumstellar disk material, they can shock the surface of the planet, and by doing so, they can generate H-alpha line emission. The last thing we can expect to see is circumplanetary disks. So stars have circumstellar disks. In similar way, giant planets, they can have teeny tiny disks around themselves, which we call circumplanetary disks. If the circumplanetary disk has a lot of dust particles, millimeter-sized particles, then we can expect some millimeter continuum emission detected with AMA. And there's this perfect case study, PDS-70, where we detect all the three signatures. So this is some basic information. It's pre-main sequence spectral type of K7 star, and it's about 0.8 solar masses in mass. It's 5 million year old, and it's about 113 parsec away from us. And again, this is the first and the only system by far where protoplanets are detected with all these three proposed observations. And this is the disk I showed earlier in my talk. You can see that there's a big cavity, right? So to give you some background on this object, so the PDS-70b, the first planet discovered in this system, was published in 2018. And what you're looking at here is near-IR image, different wavelengths, L-band, H-band, K-band, again L-band with different telescopes and different facilities, instruments. But what you consistently see here is this bright block on this side of the disk. Of course, the images are noisy, and you can see a lot of speckles. So to convince you, this is the latest image of this system taken with VLT with 2.5 hour integration, and you can clearly see there's this thing, this blob here. And you can also see the disk feature here and the inner cavity in this near IR wavelengths. So it's about 22 AU distance from the central star with few Jupiter masses. And this is now taken with Magellan with AO, mag AO. The blue is the same image as this one, and what is plotted with pink is the H-alpha emission. And the estimated mass accretion rate to this object is about 10 to the minus 8 plus or minus 1 Jupiter masses per year. So we asked for ALMA DDT observation, director's discretionary time, and these are some details if you're interested in. And this is the data, and this shows the 12CO observation, 12CO distribution on sky, and this is continuous, so you're looking at dust particles and gas. One thing I'd like to point out here is that you see this gap here, deficit in emission, which is nicely aligned with the orbit of PDS-70b, which I plotted with white dotted ellipse. So I can just do this, and you can see that there's deficit in CO emission. But what was really interesting was, if you look at the continuum ring, right, it's pretty far away from the planet, you can already tell. And you see some non-zero CO emission between the orbit of the planet and the continuum ring. And it was very hard to understand this because this is what we typically see. So one of the conclusions that we made, this is the last sentence of the actual abstract of the paper we published last year. I ran a lot of models, but I was not able to reproduce the observation because the inner cavity was too big to explain with just one planet, right? Even if you had 10 Jupiter mass planet, which is pretty large, we could not just explain the width of the cavity. So we suggest that there might be a lower mass companion within the cavity. And it turned out that it was really the case. So this is again the same observation that I showed before, and it was actually there here. It was on and off. So at that time we didn't believe that it's real, but it turned out that it is real. So this is thermal emission coming from the second planet, PDS-70C. And now what you are looking at in the middle panel is H alpha taken with VLT. You see this white block for PDS-70B, and another one here for PDS-70C. And this is all 1 millimeter continuum. You see, well, this is point source, but yeah, here's some emission 5 sigma. Here's another one at the location of PDS-C. So at this point, we are pretty convinced that these are real protoplanets. So in light of these gorgeous observations, I ran hydro simulations where I took 2 planets with 5 Jupiter masses for the inner one, 2.5 Jupiter masses for the outer one. What you are looking at here is the gas distribution in the disk. So this is vertically integrated gas distribution. And you may see sometimes planets are orbiting in clockwise, sometimes it's orbiting counterclockwise. It's not actually changing orbital direction, but because they are migrating. So the orbital period is varying over time, whereas I made output at fixed interval. So for example, I made outputs for every 1,000 years. In 1,000 years, this planet orbits one time and a little bit more in some cases, and the other time one orbit, a little bit less than one orbit. That's why it changes. It appeared to change its orbital direction. Now, what I have included here is test particles with different sizes, with different colors. These are basically millimeter-sized particles, 100 micro, 10 micro, micro, and sub-micrometer-sized particles. So I'm going to point out 2 things. First, they are very likely in mean motion resonance, in this case 2-to-1 mean motion resonance. What I plotted here is the resonance angle for 2-to-1 mean motion resonance. So if they are locked in 2-to-1 mean motion resonance, they are supposed to have this angle around 0, and you can see that, yeah, they are oscillating around 0. And it's really interesting because we know in exoplanetary system, this is HR 8799, where we detected 4 giant planets, and they are likely that they are locked in 8 to 4 to 2-to-1 mean motion resonance. So it's a chain of 2-to-1 mean motion resonances, and actually Dan is one of the first ones who proposed that they are in mean motion resonance. And this is about 30 million year old degree disk system. In the solar system, one proposed mechanism to explain the small mass of the Mars. It's a pretty small planet, right? And we don't have a lot of material in the asteroid belt. One way to explain that is Jupiter has migrated inward, so it truncated the inner disk and scattered a lot of planetesimals. And then Saturn has followed in, and then they are locked into mean motion resonance. In this case, it's 3-to-2 mean motion resonance. And in a certain case where the inner disk is more massive than the outer disk, they change the migration direction and they migrate outward together. That's one explanation for the small mass of Mars. And that's one evidence that we see these giant planets locked into mean motion resonance pretty early while the gas disk is present. The other one is that PDS-70 system provides strong observational evidence that these giant planets can block solid particle flow to the inner disk. So you can see that there are a lot of particles blocked by the 2 giant planets. And if I zoom in here, again, yellow, orange, those are large particles, 0.1 to 1 millimeter sized particles, and they are trapped at the pressure bump beyond those planets' orbit, right? Again, this is because of the aerodynamic drag. You have high pressure at this location, so particles tend to go there to the pressure peak. Now, small particles, micrometer-sized particles, sub-micrometer-sized particles, they are very well mixed to gas, so they can actually flow through the gap created by this common gap created by these 2 planets. So if you look at the inner disk, you only see green, blue, or black particles, which is basically sub-micro to 10 micrometer sized particles. Going to exoplanetary system, we now know that more than about 30% of Kepler FGK stars, those are sun-like stars, they have at least one close-in super-Earth or mini-Neptune planet, these ones, right? So the question is then why we don't have such a planet, right? Why did we fail to form a close-in super-Earth or mini-Neptune? One possibility I can suggest is that Jupiter and perhaps Saturn together could have opened a gap, and it has blocked the inward solid migration. That's one possibility. And actually, we see some meteoritic evidence by looking at the meteorites and by doing isotope measurements. We now know that there are two distinct, chemically distinct population in meteorites where cosmochemists try to explain by to have Jupiter at 5 AU opening a gap, and by doing so, it separates the disk, protoplanetary disk of the sun into two pieces, the inner disk and the outer disk, and they were not able to communicate with each other. So looking to the future, the main goal will be to use theories and observations and of course numerical simulations, but also lab experiments of protoplanetary disk and exoplanets and the solar system to improve our understanding of planet formation processes. So I will try to summarize a few projects that I am planning on. So first is orbital migration. I already mentioned about this. The question is if they are really planets. I know this is a strong assumption. If those are really planets, how they evolve over time in terms of orbital distance from the star, right? Will they stay there or will they migrate in, right? We have some evidence from Jupiter that it could have migrated, right? I showed you Grand Peng model where we try to understand the small size of Mars by allowing the Jupiter to migrate inward and then outward. That's one evidence, but there's growing evidence chemically. Actually, we knew this from Galileo and Cassini, but it is strengthened by Zuno mission. So in this recent paper by Karen Oberg, what she has done is basically looking at the composition of current Jupiter's atmosphere, atomic abundance, right? Carbon, nitrogen, argon, xenon, neon, and then those are all supersolar. So compared to solar abundance, they are supersolar. So if you just form in protoplanetary disk that has the same composition as the current sun's atmosphere, right? You cannot really explain the composition. What she proposed was that the core of Jupiter has to have formed very far away from the star. In her case, in her paper, she suggested it has to form have formed beyond N2 snow line, nitrogen snow line, which is 40-45 AU in the protoplanetary disk of the sun. So you form the core at 40-45 AU, which is actually interestingly at this point where we see a lot of rings and gaps. And at that point, the core should have been about a tenth or a little lower than tenth of the Jupiter's mass. So you start from at this location, and it has migrated all the way into current location of Jupiter and has grown to 1 Jupiter mass. So we have some sort of evidence from Jupiter. So it is one interesting question. And I have been working with my grad student. So if you think about migration and how it works, you need to basically calculate the torque from the inner disk and the outer disk. And if you think about torque, it's R cross F, where F is the gravity, simply in this case. And it goes to 1 over R squared, where R is the distance. So it means that torque is proportional to 1 over distance. So what matters the most is the structure very close to the planet. And we are trying to understand how the disk thermodynamics could invert the migration direction or not, and how that affects the migration rate. And also, we have been doing these orbital migration simulations for a long time, right? But we are limited in 2-dimensional simulations, and that is because these are numerically expensive to run for millions of years. Now we are at the point where we can actually try to start running these things in 3 dimensions with growing facilities, and there is very interesting implication when you include 3 dimensions in protoplanetary disks. observationally, I have already shown this, and you might have noticed there's this kinematics, right? So you might have wondered what does that mean when you say exoplanet detection and this kinematics, right? So this is the line observation, CO line observation of HD 163-96. And if you look at this particular channel here, I'm going to zoom in. This is the same channel. If you look at this part, you see something is distorted, right? This is not very smooth. So what's happening here is you're basically looking at a certain velocity channel. So basically, if there's nothing happening, right, you would expect to see very smooth iso velocity contour, but that's not what is happening here. If you draw iso velocity contour, this is one and this is the other, and that's broken. So the interpretation for this feature is that if there is a planet right at the middle of this break, right, then you can expect those with spiral wakes, because spiral wakes are the strongest at the vicinity of the planet. And this is what actually made this kinematics part of the exoplanet demographics figure. So here you see this velocity kink, the broken feature in CO emission, where we see this, where we propose that there's a planet, Jovian-mass planet, and it's really nice, and this method can be strong because when you compare this with continuum disk, this is continuum and this is line emission, that exactly falls in the gap in the millimeter continuum. So if you just had continuum image of this object, right, there is a gap, there might be a planet, right, but even if there's a planet, where would you put within this gap, right, we have no idea, right, but now it is localized signature, so if you want to follow up this object, then you can really know where to go in the disk. So this is a strong new method. And the last thing is that go to the first place, right? How does protoplanetary disk form, right? How the forming star and disk system obtain mass from its vicinity, and what are the initial conditions for protoplanetary disk evolution and planet formation? And if you are more interested in substructures, at which evolutionary stage do they form, right? So this is the seminal paper by Frank Xu, where he introduced this self-similar collapse of isosomal sphere, right? So you have this molecular cloud, onion ring shaped cloud, where you have more angular momentum in the outer part of the sphere, less angular momentum. So the inner part of the molecular cloud falls into the star, and the next part falls into the inner disk. The middle part makes the middle part of the disk. It's a smooth, constant isotropic process, right? It has been just standard for many decades. But maybe that's not the case. So this is again HL tau system, and this is the HL Hubble image of HL tau, and you can see that the disk is embedded within a nebula. And this is again HL tau image taken with ALMA in continuum. But if you look at, in this case, HCO plus, this is where we see millimeter continuum. You see this spiral falling onto the disk because you know what the velocity is for this stream. You can tell if that's within the disk or it's falling into the disk from outside of the disk. And it turns out that this is actually an infalling stream to the disk, so it's not symmetric configuration. This is another example, L1449 ILS. This is also an embedded disk. This is ALMA image, in this case C18. So you have this disk, but you have this spiral infalling stream, and the other side you have another counterpart of the infalling stream. And this is now a numerical simulation run by Matthew Bate. So what he has done here is, this is basically a star formation cluster simulation. So you can think of Orion or Taurus, where you form tens or hundreds of stars pretty quickly by collapsing those giant molecular clouds. And each panel here represents one star in that simulation, and zoom in around the stars, right? And they form this, but if you stare at any of these panels, right, you will notice that there is no simple isotropic collapse to star and disk. They are very violent, they have a lot of flybys, and there are a lot of streams falling onto the disk. It's not a simple process. So both observations and numerical simulations point that the mass addition is probably not isotropic, and it can be episodic, which is different from the view that we have long been have. So to address this question, we have ALMA large program where this is accepted last cycle. Large ALMA program where we proposed to look at 17 embedded disks. So those are like HL tau or younger version of HL tau. So we will get continuum and CO data for 17 disks with the resolution of comparable to D-sharp survey. This is the continuum survey that I introduced at the very beginning. So it's great. We will be having a lot of data, and this is a great data set for grad students if interested to start with. So to summarize my talk, this is really exciting time to study plan information because the field has been really dominated by theories and numerical simulations for decades. But now we can really test and improve those theories with observations. A couple of points that I made with my work is we see a lot of these substructures using ALMA observations or ground-based observation with AO, but well, planet is one intriguing possibility, but you cannot really conclude that those are formed by planets until you really detect planets themselves. But when you detect planets themselves, you can learn a lot about how planets form, how planets would evolve within protoplanetary disks. And I will just briefly mention about this figure again to show that the future is bright and exciting. This is what we currently have, different exoplanet techniques with different colors. We will have RV, if we can achieve 10 centimeters per second precision, right? This is currently meters per second. And if we can monitor for a decade or longer, then this boundary will be pushed down and outward. And there will be W first, which we believe we can probe this broader region in semi-major axis and planet masses, semi-major axis and planet masses. And we also have JWST. We hope that it launches. So if it launches, then we can detect some, directly detect some giant planets out there. And of course there's GMT, TMT, European ELT, which will basically probe this region of the primary space. And there are NGVLA, next generation VLA. This is an extended version of VLA. Also flagship missions proposed like HABX, Origin Space Telescope, and LUVOIR, which will probe a lot of, which will bring us a lot of new exoplanets. So in the future, in the next decade, 2 decades, this region of the primary space will be populated by both protoplanets and exoplanets, and it will be really exciting. Okay, I'll stop here and take any questions.
Thank you, Steve. Questions?
I really like this plot, and I'm curious about that really low mass planet that you referred in the disk, and it makes me wonder how low mass can you go and still see? Yeah, that one.
Yeah. So I included this one just to make the plot complete. So when we do forward modeling, right, we make a lot of different assumptions, and they may not agree with each other, right, in some cases. And I personally believe that this is a little bit too low mass, to be honest. But yeah, it is published, it's out there, so I try to include that and try not to neglect anyone's work.
So I'd like to ask a follow-up to that, which is,
Sure.
If we, have different groups analyze the same data sets and reach the same conclusions?
That's one thing we are trying to do actually. So we had a workshop, which I was part of the SOC last October, where we brought simulators, modelers, as well as ARMA observers. We were trying to, sit down together and trying to see what's different between codes and with different approaches, what we are using. That's certainly something we are trying to do, but so far, no.
I like seeing the students asking questions. We're going to keep going with the students. Bill?
So if you take repeat observations of these systems that have spirals, would you be able to see them evolve with time?
Yeah, there's actually one paper where people actually did that exact one. The problem is, the overall time scale is pretty long. So
Right.
these are tens or 100 AUs. If you think about 100 AU on solar solar mass star, one of your time is 1,000 years. I mean, it's not impossible, it's doable, but it takes many years to do that. But yeah, I'm sure, yeah, we will be getting there. So.
And one more student question. Yes.
Are these disks turbulent?
Yes and no. Well, it is turbulent, of course, but well, the question is if it's turbulent, how much turbulent, right? So the general consensus right now, I don't know if you're familiar with this alpha scheme, alpha turbulence. We thought that in 1980s, 1990s, by looking at how much mass should be accreted onto the star over a lifetime of from the planetary disk, which is basically a few million years, we believe that alpha, in terms of alpha value, of course alpha is not perfect, but in terms of alpha, we believe that it is about 0.01. We now believe that it is not anywhere close to 0.01. You can actually observationally constrain by looking at molecular lines and how much non-thermal broadening you have in those lines, right? You have certain temperature, you will see Gaussian profile, right? On top of that, do we see anything else? And currently, we have only upper limits. But in terms of alpha, it's below 10 to the minus 3. So yeah, it can be turbulent. There are mechanisms to generate turbulence, but not so much.
Baker, thanks for your patience.
So I was just wondering, you showed that a single planet can give you spiral arms, you can have multiple, so it's very hard to tell. And yet in your figure right here, you have complete like planet mass versus semi-major axis, and there's no, I presume there's some degeneracy in the parameters and you can't really get all these very well. How well do you actually know this? Or?
That's a great question. Well, before that, the strongest assumption is that these are created by planets, which we don't know for sure, right? So that's the strongest assumption. Now, if you have observations, you can, well, what matters for these structures is first, the underlying disk structure, the most important one is the temperature, and that is because waves, these are sound waves, acoustic waves, which means that the propagation speed depends on the temperature profile of the disk. So temperature matters. The other thing is viscosity, how viscous the disk will matter, because it's really viscous, then you want to open the planet, or you want to open the gap in the first place. And the width and the depth of the gap will be dependent on the viscosity. So temperature, planetary mass, and viscosity, they are three major things. What we have been doing is to run a lot of simulations varying those parameters and get some empirical relationship between those parameters. For these ones, we constrain the temperature structure, so we are confident that we get some sort of accurate temperature profile. Now there are two variables, planetary mass and viscosity, and we empirically know that planetary mass and alpha value is proportional to something like m planetary mass goes to square root of alpha. So if you believe alpha is uncertain by a factor of 10, then that gives you a factor of 3-ish uncertainty in terms of mass. So if you look at these population, for example, 0.1 Jupiter mass is suggested here. They can be, say, Saturn mass, or it can go down to Uranus or Neptune mass, but they are probably not like Earth mass or Jupiter mass.
So you think it's a 30% or, I mean,
A factor of
3 times error?
Yeah, a factor of 3.
All right, I was waiting for you.
I have a couple of questions.
Sure.
One is you mentioned very tantalizing prospects of looking at circumplanetary disks. I was wondering if there is actually any evidence or anything that you already know. And the other question had to do with if we had polarization data, what more would we be able to get from that?
Right. So these are 5 sigma detections we presented last year, and then we asked again another DGT time to confirm the existence of CPDs which we are in preparation. As far as I can tell right now, we have, at least for PDS-70C, we have redetected at the same location. So we are confident that this is real. we'll have to do some more, some deeper calibration to see, because this is a weaker signature. So we need to do some more, deeper calibration to conclude that if this is real or not. But at least PDS-70C, we are confident that there are linear ruconium emission coming from that location. Of course, if you're asking if that's really coming from CPD or something else, well, yeah, we don't have an answer for that yet. But there's one way to do that. If you look at gas data, right, and see what velocity component you have there, right, you can expect to see, for example, if Jupiter mass, then you have Keplerian rotation around the Jupiter mass object, and you will get Keplerian rotation in that disk. So if we use gas velocity, then you can figure out if it's really a disk around the planet or something else.
You'd have the resolution for that.
Yes, so in this case, this is the resolution element, the beam size. So this is about the size of the CPD, which we expect from numerical simulations. The one we asked for the DDT data, which is not published yet, we have about a factor of 2 or 2.5 better spatial resolution. So we believe that, yeah, that's sufficient to spatially, yeah.
What about the question about polarization?
Right, that's an interesting question which I'm not directly working on. Did you mean polarization for CPDs or in general circum?
General, well, I know there's been some work on HL tau disk, but not just.
Yeah, so one thing about polarization I can tell, I'm not an expert and I'm probably not the best person to answer this question, but polarization, you expect for particles to align or not with respect to magnetic fields, right? So if you can tell, if we see some polarization pattern, then you can tell something about if there's a magnetic field, if so, how strong those are, and you can also perhaps constrain size distribution of those the particles in the disk by looking at polarization at different wavelengths.
Last question for Wendy.
So in your last slide, I was a little surprised to see the conservative limits that you had for the ELTs. And certainly one of the scientific justifications for GCLEF on GMT is rate of velocity of 10 centimeters per second and being able to detect Earth mass planets.
Right.
So I'm just curious to know why you...
So you're asking about ELT, these ones?
Yeah.
Yeah, well, it's glad to hear that you think this is conservative. That means that you can do better than that.
I
Right?
hope so.
Well, that
Unless
must be,
something's changed.
that must be from direct imaging. That must be the prediction of
Yeah,
optical or infrared direct imaging.
yeah, right.
So GCLEF would be the yellow line.